welcome to this problem walkthrough. Today, we'll be tackling the problem number 2208 titled Minimum Operations to Have Array Sum. This problem challenges us to think critically about reducing an array's sum efficiently using halving operations. Stay tuned as we explore the intuition, strategies, and implementation details. In this problem, we're tasked with reducing the sum of a given array of positive integers by at least half of its original value. To achieve this, we can perform an operation where we select any number in the array and reduce it to half of its current value. The goal is to determine the minimum number of such operations required to meet this condition. For input, we have an integer array called nums, which can have up to 100,000 elements, with each element ranging from 1 to 10 million. The output will be a single integer representing the minimum number of operations needed. This gives us a clear framework for the problem, and we'll explore examples to better understand how this works in practice. Let's look at the first example. Here, the input array is 5, 19, 8, 1. The initial sum of this array is 33, and our target is to reduce the sum to at most 16.5, which is half of 33. We start by choosing the largest number, 19, and reducing it to half, resulting in 9.5. This reduces the sum to 23.5. Next, we take 9.5 again and reduce it to 4.75, which brings the sum down to 18.75. Finally, we reduce the next largest number, 5, to 2.5, lowering the sum to 16.25. At this point, the sum is less than or equal to 16.5, so we stop. The total number of operations performed is 3, and that's our result for this example. Now, consider the second example where the input array is 3, 8, 20. The initial sum here is 31, and our target is to reduce the sum to no more than 15.5. We begin with the largest number, 20, and reduce it to 10, which brings the sum to 21. Next, we reduce 10 again to 5, lowering the sum to 16. Finally, we reduce 8 to 4, resulting in a sum of 12, which meets our target. The total number of operations needed here is also 3, and this demonstrates how the process works for a different input. There are a few important constraints and edge cases to consider. First, the array can be as small as one element or as large as 100,000 elements, with values ranging up to 10 million. This means our solution needs to handle both small and large inputs efficiently. Edge cases include scenarios like small arrays, such as 1, or 2, 3, where the solution must handle minimal input sizes. For large arrays, like one with 100,000 elements all equal to 10 million, the algorithm must be optimized to process such inputs quickly. Another edge case is when the sum is already less than or equal to the target, such as 1, 1, 1, where no operations are required. Finally, uneven distributions, like 1, 1, 1, 10 million, test whether the solution prioritizes reducing the largest values first, as this is critical for minimizing operations. To begin, let's consider the different approaches we could use to solve the problem. The first option is a brute force approach. The intuition here is straightforward. We iterate through all possible combinations of halving operations for the numbers in the array, checking if the array's sum is reduced to at least half of its original value. This involves repeatedly halving each number and testing the condition at every step. However, while this method is conceptually simple, it is extremely inefficient. The time complexity grows exponentially, 2 to the power of n, because we explore all possible combinations of halving operations. This makes it impractical for larger arrays, as the number of possibilities grows too large to handle efficiently. It's a method that might work for very small inputs, but it quickly becomes infeasible as the size of the input increases. On the other hand, there is a more refined approach, a greedy strategy using a max heap. The key insight here is that the largest numbers in the array contribute the most to the sum, so having them will have the greatest impact. By prioritizing these numbers, we can minimize the number of operations required. To implement this, we first calculate the total sum of the array. Then, we insert all the numbers into a max heap to track the largest values efficiently. From there, we repeatedly extract the largest number, halve it, and add the halved value back into the heap, while keeping track of the reduced sum and the number of operations. This process continues until the sum is reduced to at least half of its original value. The complexity of this approach is much better than brute force, building the heap is O, n, and each halving operation involves O, log n, for heap adjustments. In the worst case, where every number might need to be halved multiple times, the overall complexity becomes O, m asterisk log n, where m is the total number of halving operations performed. Now, let's discuss the trade-offs of the greedy approach with a max heap and why it's the chosen strategy. This method is not only efficient but also scales well with larger input sizes. By focusing on the largest numbers first, we avoid unnecessary computations and directly target the elements that have the greatest impact on the array's sum. This targeted strategy ensures that we achieve the desired result in the fewest operations possible. The key insight here is that the largest numbers dominate the sum, and their contributions decrease rapidly with each halving operation. Using a max heap allows us to efficiently access and process these numbers, maintaining an optimal balance between speed and simplicity. Compared to the brute force approach, the greedy solution offers an exponential improvement in efficiency. While other methods, such as sorting the array and iteratively having the largest numbers, might also work, they lack the performance benefits of the heap-based solution. Repeatedly sorting the array would introduce additional overhead, making it less optimal. The max heap approach, therefore, stands out as the best choice, combining clarity, performance, and correctness to solve the problem effectively. Finally, let's summarize the trade-offs and comparisons between the approaches discussed. The brute force method, while simple to understand, is computationally prohibitive for larger inputs due to its exponential time complexity. The greedy approach with sorting is easier to implement than a heap-based solution, but it suffers from inefficiencies caused by repeated sorting operations. On the other hand, the greedy approach with a max heap is the most efficient and scalable option. It allows us to dynamically track and process the largest elements in the array without redundant operations, making it the ideal strategy for tackling this problem. In conclusion, the heap-based greedy approach strikes the perfect balance between clarity, performance, and correctness. It leverages the problem's key insight, having the largest numbers first, to minimize the number of operations required and ensure the solution is both practical and optimal for a wide range of input sizes. In this problem, we are tasked with reducing the sum of an array to at least half of its original value using the minimum number of operations. Each operation allows us to have the value of any one element in the array. For example, having the number 8 gives us 4, and having 4 again results in 2. The key is to minimize the number of these halving steps. To achieve this, we adopt a greedy approach where we always target the largest numbers first, since having the largest element will have the most significant impact on the sum reduction. To implement this efficiently, we use a max heap, which allows us to quickly access and process the largest element at each step. As we have the largest number, we subtract the halved value from the current sum and push the halved value back into the heap so it can be halved again later if needed. This process is repeated until the total sum is reduced to at least half of its original value. The greedy strategy is central to this problem, as having the largest number in the array reduces the sum the fastest and minimizes the total number of operations. To efficiently implement this strategy, we use a max heap, which allows us to quickly retrieve the largest number in O(1) time and supports insertion and removal operations in O log n. The stopping condition for the algorithm is when the cumulative reductions we achieve bring the current sum down to at least half of the original sum. This ensures we stop as soon as the goal is met. To manage this, we store all elements of the array in the max heap by inserting their negative values, because Python's heap module is a min heap by default. By using negative values, the smallest number in the heap corresponds to the largest original number. Throughout the process, we also maintain a variable to track the current sum of the array after each halving operation. Let's break the algorithm into detailed steps. First, we initialize our variables. We calculate the original sum of the array, which we'll call original_sum, and determine the target half_sum by dividing original_sum by 2. We then create a max heap by pushing the negative values of the array elements into it. This ensures the largest original value is always at the top of the heap. We also initialize current_sum to keep track of the running sum and set operations to 0 to count the number of halving steps performed. The main halving process begins with a loop that continues as long as current_sum is greater than half_sum. Inside the loop, we extract the largest element from the heap, have its value, update the current underscore sum by subtracting the halved value, and push the halved value back into the heap. Each time we perform this sequence, we increment the operations counter. The algorithm terminates when the current sum becomes less than or equal to the target half sum. At this point, we return the operations counter as the result, which represents the minimum number of halving steps required. Now, let's analyze the key operations. Constructing the max heap from the array takes n time. Each halving step involves extracting the largest element and reinserting the halved value, which are both log n operations. If k is the total number of halving steps, the overall complexity of the algorithm is n plus k asterisk log n. This is efficient given that k is typically much smaller than n in most practical cases. We also need to handle some edge cases. For example, if the array contains only one element, we simply have it repeatedly until it meets the condition. If the original sum is already less than or equal to half the target, no operations are needed, and we return 0. Finally, we ensure that having large numbers doesn't cause overflow issues. Let's walk through an example to understand how the algorithm works. Consider the input array 10, 20, 7. First, we calculate the original underscore sum, which is 37, and determine the half underscore sum as 18.5. We initialize the max heap with the negative values of the array, resulting in -20, -10, -7, and set current underscore sum to 37. The operations counter starts at 0. In the first iteration, we extract the largest element, which is 20. Having 20 gives us 10. We subtract 10 from current underscore sum, reducing it to 27, and push -10 back into the heap. The heap now looks like -10, -10, -7. We increment the operations counter to 1. In the second iteration, we extract 10, have it to 5, and subtract 5 from the current underscore sum, reducing it to 22. We push -5 back into the heap, making it -10, -7, -5, and increment operations to 2. In the third iteration, we again extract 10, have it to 5, and subtract 5 from the current underscore sum, reducing it to 17. We push -5 back into the heap, resulting in -7, -5, -5, and increment the operations counter to 3. At this point, the current underscore sum is 17, which is less than the half underscore sum of 18.5, so the loop terminates. We return the operations counter, which is 3, as the result. This example highlights how the greedy approach efficiently reduces the sum by focusing on the largest numbers. The max heap plays a crucial role in ensuring the largest element is always processed first, while the halving operations maintain the focus on minimizing the total number of steps. By targeting the largest numbers, we rapidly reduce the sum, meeting the condition in the fewest possible operations. Here, we start by importing the heap library, which will help us manage a heap structure. Then, inside the haveArray function, we calculate the total sum of the input array nums and determine the target sum, which is half of the total. The goal is to reduce the current sum of the array to this target. To efficiently manage the largest numbers in the array, we use a max heap. However, since Python only supports min heaps by default, we negate all the values in the array to simulate a max heap. The heap.heapify function then transforms the list into a valid heap. We initialize two variables, reduced underscore sum to track how much of the total sum we've reduced so far, and operations to count the number of halving operations performed. Next, we enter a while loop that continues until the reduced sum meets or exceeds the target. At the start of each iteration, we extract the largest value from the heap, negating it back to its positive form since the heap contains negative values. Once we have the largest value, we have it and push the halved value back into the heap, negating it again to maintain the max heap property. We then add the halved value to reduced underscore sum to update our progress and increment the operations counter. The loop continues this process until the sum of all reductions meets or exceeds the target value. Finally, we return the total number of operations performed. This approach ensures we always target the largest value for halving, minimizing the number of steps required to achieve the goal. Here, we start by importing the priority queue class, which will be used to implement a max heap. Inside the solution class, the method haveArray is defined to take an integer array as input. First, we calculate the total sum of the array using a for each loop, summing up all the elements. This total sum is then divided by 2 to determine the target value, which represents the threshold we need to reduce the array sum to. Next, we initialize a max heap using a priority queue. Since priority queue in Java defaults to a min heap, we reverse the order by providing a custom comparator that compares elements in descending order. We then iterate through the array, adding each element to the heap as a double to ensure precision when performing division operations. To begin the halving process, two variables are initialized: reduced sum, which tracks the cumulative sum of the values we've halved, and operations, which counts the number of halving steps performed. The while loop begins, running as long as the reduced sum is less than the target. Inside the loop, we extract the maximum value from the heap using the poll method, which removes and returns the largest value. The largest value is then halved by dividing it by 2. This halved value is immediately added back to the max heap to ensure the heap reflects the updated values. Next, we update reduced sum by adding the halved value, effectively tracking how much of the total sum has been reduced so far. At the same time, the operations counter is incremented to record the halving operation that was just performed. The loop continues until reduced sum reaches or exceeds the target, ensuring that the array's total sum is reduced to half or less. Finally, the method returns the operations count, which represents the minimum number of halving operations required to achieve the desired reduction. This implementation efficiently handles the problem by leveraging the max heap to always target the largest value for halving, minimizing the number of operations. To begin solving this problem, we start with the array nums equals 5, 19, 8, 1. First, we calculate the total sum of the array, which is 5 plus 19 plus 8 plus 1 is equal to 33. Our goal is to reduce this sum to half, which is 33 divided by 2 is equal to 16.5. To efficiently track and reduce the largest elements in the array, we use a max heap. Since Python's heap library only supports min heaps, we simulate a max heap by negating all the values. This gives us the initial heap as -19, -5, -8, -1. The reduced sum is initialized to 0, and the operation count is also set to 0. Now, we proceed with the step-by-step execution. First, we heapify the array, which organizes the negated values into a valid max heap structure, remaining as -19, -5, -8, -1. Next, we extract the largest value, which is 19. Having this gives 19 divided by 2 is equal to 9.5, and we add -9.5 back to the heap. Our heap becomes -9.5, -8, -1, -5, after this operation. The reduced sum is updated to 9.5, and the operation count is incremented to 1. Extracting the largest value again, which is now 9.5, we have it to get 4.75, add -4.75 back to the heap, and update the heap to -8, -5, -1, -4.75. The reduced sum now becomes 14.25, and the operation count increases to 2. Finally, we extract the largest value, 8, which when halved gives 4.0. Adding -4.0 back to the heap results in the heap structure becoming -5, -4.75, -1, -4.0. The reduced sum is updated to 18.25, which surpasses our target of 16.5. At this point, we stop as the condition is satisfied. The total number of operations required is 3. This completes example 1, where the final output is 3 operations. Now, let's move on to example 2 with nums equals 3, 8, 20. The total sum of the array is 3 plus 8 plus 20 is equal to 31, and the target sum we need to reduce to is 31 divided by 2 is equal to 15.5. Again, we use a max heap initialized with the negated values of the array, giving us -20, -8, -3. We begin by heapifying the array, which organizes the negated values into a valid max heap structure remaining as -20, -8, -3. The reduced sum is set to 0, and the operation count starts at 0. Extracting the largest value, which is 20, we have it to get 10.0 and add -10.0 back to the heap. This updates the heap to -10.0, -3, -8. The reduced sum is updated to 10.0, and the operation count becomes 1. Next, we extract the largest value, 10.0, have it to 5.0, and add -5.0 back to the heap. The heap now becomes -8, -3, -5.0, and the reduced sum increases to 15.0, with the operation count incrementing to 2. Then, we extract the largest value again, which is 8, have it to 4.0, and add -4.0 back to the heap. This results in the heap structure becoming -5.0, -3, -4.0, and the reduced sum now reaches 19.0, exceeding the target of 15.5. At this point, the condition is met, and the total number of operations required is 3. The final output for example 2 is therefore 3 operations. Now, let's analyze example 3 with nums equals 1, 2, 3, 4, 5. The total sum of the array is calculated as 1 plus 2 plus 3 plus 4 plus 5 is equal to 15. The target sum to reduce to is 15 divided by 2 is equal to 7.5. Using the same approach, we initialize a max heap with the negated values of the array, resulting in -5, -4, -3, -1, -2. Heapifying this array organizes it into a valid max heap structure, which remains as -5, -4, -3, -1, -2. The reduced sum is initialized to 0, and the operations count starts at 0. Extracting the largest value, which is 5, we have it to get 2.5 and add -2.5 back to the heap. The heap becomes -4, -2.5, -3, -1, -2, and the reduced sum is updated to 2.5, with the operation count incrementing to 1. Next, we extract the largest value, 4, have it to 2.0, and add -2.0 back to the heap. This updates the heap structure to -3, -2.5, -2, -1, -2.0, and the reduced sum increases to 4.5. The operation count is increment to 2. We then extract the largest value, which is 3, have it to 1.5, and add -1.5 back to the heap. The heap becomes -2.5, -2.0, -2, -1, -1.5, and the reduced sum is updated to 6.0, with the operation count increasing to 3. Extracting the largest value next, which is 2.5, we have it to 1.25 and add -1.25 back to the heap. The heap updates to -2.0, -1.5, -2, -1, -1.25, and the reduced sum becomes 7.25. The operation count is increment to 4. Finally, we extract the largest value, 2.0, have it to 1.0, and add -1.0 back to the heap. The heap now becomes -1.5, -1.25, -2, -1, -1.0, and the reduced sum reaches 8.25, exceeding the target of 7.5. The total number of operations required in this example is 5, and the final output is 5 operations. Here, we analyze the time complexity of our solution. First, we need to convert the input array into a max heap. This process, known as heapification, is performed in O(n) time, where n is the size of the array. Once the heap is built, the halving operations begin. In each step, the largest value is removed from the heap, halved, and then pushed back into the heap. Both the removal and insertion operations take O log n time because the heap needs to maintain its structure. The number of iterations depends on how quickly the sum of the halved values reaches half of the total sum. In the worst case, this can take O(n*log, max, nums, iterations, or max, nums, represents the largest value in the array. This is because the largest value decreases geometrically as it is repeatedly halved, and the number of steps required is proportional to log, max, nums. When combining these components, the overall time complexity is O(n plus n*log, max, nums. For large inputs, the halving operations dominate the total time complexity. Now, let's focus on the space complexity of the solution. The primary space usage comes from the max heap, which stores the halved values of the elements. Since the heap contains one entry for each element in the input array, it requires O(n) space. Additionally, the solution uses a small, constant amount of space for auxiliary variables such as total_sum, target, reduced_sum, and operations. These variables do not depend on the size of the input, so their space usage is O(1). When we consider these factors together, the overall space complexity is dominated by the heap, resulting in O(n). Let's compare this heap-based solution to a brute force or naive approach. In a naive solution, the array would be sorted after every halving operation to repeatedly identify the largest element. Sorting the array takes n log n per iteration, and the number of iterations could still be proportional to log max nums. This results in a time complexity of n log n asterisk log max nums. In contrast, the heap-based solution is significantly more efficient because it avoids the need to repeatedly sort the array. From a mathematical perspective, the halving process reduces the largest value geometrically, meaning the number of operations is proportional to log max nums. Since each heap operation, such as a push or pop, takes log n, and there are at most n elements in the heap, the overall time complexity is n asterisk log max nums. This makes the heap-based method a clear improvement over the naive approach. Finally, let's break down the best, average, and worst-case scenarios for this solution. In the best case, the target is achieved after only a few halving operations. Here, the time complexity is dominated by the heapify step, which takes n. In the average case, for typical inputs, the number of iterations required is proportional to log max nums. Combining this with the heap operations, the time complexity becomes n plus n asterisk log max nums. In the worst case, when the sum decreases very slowly, the complexity remains n plus n asterisk log max nums. Across all cases, the space complexity stays consistent at n, as the heap remains the primary contributor to space usage. Now let's look at some common mistakes candidates make when tackling this problem. First, failing to properly calculate the original sum. Sometimes, the sum of the array is either calculated incorrectly or not stored before making modifications. This can lead to errors when comparing if the sum has been reduced by half. The solution is simple: always store the original sum at the very beginning and make sure all checks reference this stored value. Next, a frequent issue is not prioritizing the largest elements when halving. Having elements randomly or sequentially is inefficient because reducing the larger numbers first has a greater impact on the total sum. To fix this, use a max heap or priority queue to ensure you're always having the largest element. Lastly, incorrect heap operations can cause problems. For example, forgetting to push the updated value back into the heap after halving means that critical updates are missed. To avoid this, always reinsert the halved value into the heap to maintain accuracy in subsequent operations. Let's cover a few more mistakes to watch out for. Off by one errors in counting operations are quite common. For example, you might miscount how many halving steps were performed, especially in edge cases where the initial sum is already less than half. The fix here is to carefully initialize your operation counter and ensure it increments only when an element is halved. Another major pitfall is implementing the solution inefficiently. Some candidates use nested loops or sort the array repeatedly to find the largest element, which significantly increases time complexity. This can push your solution from n asterisk log n to n squared, which is unacceptable for larger input sizes. To address this, always leverage a max heap. It ensures that finding and having the largest element is both efficient and scalable, operating in logarithmic time for each step. Understanding the fundamental insights behind this problem can set you apart in an interview. The first key insight is that this is a greedy optimization problem. The goal is to maximize the reduction in the sum with every operation, making a max heap the natural choice. The second insight is the importance of understanding heaps. You should be prepared to explain how a max heap works, including how it consistently provides the largest element efficiently. The third point is to articulate the trade-offs between brute force and optimized solutions. While brute force methods are easier to conceptualize, they're computationally expensive because they involve repeated evaluations. The heap-based approach, on the other hand, minimizes redundancy and is far more efficient. Finally, don't neglect edge cases. Arrays with a single element, arrays where all elements are equal, or cases where the sum is already less than half should all be tested to ensure your solution handles them correctly. This problem also relates to several others on LeetCode that involve heaps and greedy strategies. For example, in LeetCode 703, kth largest element in a stream, the focus is on using a heap to efficiently track the kth largest value as new elements are added. Similarly, LeetCode 215, kth largest element in an array, uses a heap-based approach to find the kth largest value in a static array. Another related problem is LeetCode 1338, reduce array size to the half, which applies a greedy heap method to reduce the size of an array instead of its sum. Finally, LeetCode 1046, last stone weight, uses a max heap to repeatedly reduce the size of the largest elements until a specific condition is met. Solving these problems can deepen your understanding of heap operations and their applications in greedy algorithms. Finally, let's explore some alternative approaches and their trade-offs. One option is a sorting-based approach. Here, you sort the array in descending order and then iterate through the elements, having the largest ones until the condition is met. While this method has an initial time complexity of n*log n for sorting, repeatedly sorting the array after each operation increases the overall complexity, making it inefficient compared to a heap-based solution. Another approach is greedy simulation without a heap. In this method, you manually find the largest element during each iteration and have it. While this avoids the space overhead of a heap, it's computationally expensive, with a time complexity of n squared due to repeated scans. Lastly, there's the dynamic programming approach. This involves pre-computing possible sums after having operations and checking if any sequence of operations reduces the sum by half. However, this method is overly complex and often has exponential time complexity, making it impractical for large inputs. Each approach has its use cases, but the heap-based solution remains the most efficient and scalable for this problem. Thank you for watching. To wrap up, we explored a powerful use of heaps to solve this problem efficiently, focusing on greedy techniques. Remember to practice similar problems to strengthen your understanding. Like and subscribe for more videos, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!